Hello, in this video we're going to talk about linear combinations, and we're going to start off with an example in R3, and then we're going to look at some more generalized vector spaces. So recall the definition of a linear combination. A linear combination of vectors v1, v2, and so on is a sum of scalar multiples. In other words, it looks like c1 times v1 plus c2 times v2 plus so forth, where those c sub i's are scalars, and for us our scalars come from the real numbers. So let's look at an example. We want to know if the vector u, can u be written as a linear combination? So that means sum c1 times vector v1. Can it be written as a linear combination of vectors v1, v2, and v3? And to figure this out, we would need to set up what we're looking at. We're looking at the vector 8, 0, 5. Can that be written as some scalar c1 times the column vector 1, 2, 3 plus some scalar, we'll call it c2, times vector v2, which looks like 0, 1, 4, plus a scalar c3, which looks like 2, negative 1, 1. So this is the same as asking, does u lie in the span of vector v1, v2, and v3? So that's the same kind of question that we are addressing here. Does this vector lie in the span? Okay, so after doing some scalar multiplication and adding up our vectors, what we really get here is we get 8, 0, 5, and then on the right hand side we get in the top row 1c1 plus 0c2 plus 2c3, and in the second row 2c1 plus 1c2 plus a negative 1c3, and in the third row 3c1 plus 4c2 plus 1c3. And that leads us to consider an augmented matrix 1, 0, 2, 2, 1, negative 1, 3, 4, 1, with these constants 0, 8, 0, 5. Okay, so let's take a look at this. We have our leading 1 in the first position. Let's now multiply a negative 2 times row 1, add it to row 2, and put it in row 2. And similarly, we'll do another operation. We'll go negative 3 times row 1, add it to row 3, and put the result in row 3. And after doing those operations, our top row stays unchanged. Our next row, once we multiply the top by a negative 2, we will get a 0, 1, negative 5, and a negative 16. And then when we multiply by a negative 3 on that top row and add it to our third row, we'll get a 0, 4, negative 5. Negative 3 times 8 is negative 24, plus 5 looks like a negative 19. So our first column looks good, and now moving on to the second column, we have our leading 1. The only thing we need to get rid of is that 4. So let's multiply negative 4 times row 2, add it to row 3, and put the result in row 3. And I'll put that down below. So top row stays unchanged. Second row stays unchanged. And now our third row is going to be a 0, 0, and now we have a positive 20 minus 5 gives us 15. And now we have a negative 16 times a negative 4 is going to give us 64. And so we've got a 64 minus 19, so that's going to give us a 45. Okay, let's keep going. Second column looks good. In this last column, or in this last row rather, let's divide by 3 or multiply by 1/3. And so we get a 0, 0, 1, 3. All right, we're almost done. So let's multiply a 5 times row 3, add it to row 2, and put the result in row 2. And similarly, let's multiply the bottom row by -2. Add that to row 1 and put the result in row 1. And after we do that, let me make a little bit of space here. Oops. There. So after we do that, we will have bottom row is unchanged. Our second row is going to be a 0, 1, 0. And we're going to have a 15 plus a negative 16 gives us -1. And then our top row is going to be 1, 0, 0. And then in that last fourth column, we'll have a -6 plus 8. That'll give us 2. And so what were we solving for? It's always important to go back and look what we were solving for. We were solving for these scalars C1, C2, and C3. And so this tells us that C1 is 2, C2 equals -1, and C3 equals 3. Okay, back to the original question. Determine whether the vector can be written as a linear combination. The answer is yes. So we'll say yes. U can be written as a linear combination of vector v1, v2, and v3. Here are the scalars that would do that for us. And so another way of saying this is that U lies in the span. So U lies in the span of those vectors. Okay, let's shift gears slightly and take a look at an example related to matrices. So this question asks us, determine whether this matrix A can be written as a linear combination of B, C, and D. So by definition, this is asking us, can we find scalars such that A equals C1 times matrix B, or vector V. These are vectors in M22, plus another scalar times C plus another scalar times D. Do those scalars exist? And so to solve this, we would need to set up -1, 7, 8, -1. That's our matrix for A. C1 times B, so this would give us C1, 0, 2C1, and C1. And for C2, we would have 2C2, -3C2, 0, and 2C2. And lastly, C3 multiplying times matrix D gives us 0, C3, 2C3, and 0. This gives us some equations. Notice in this first row, first column of every matrix, we are forced to have -1 equaling C1 plus a 2C2. Next, for the first row, second column, those must sum. In other words, we must have 7 equals -3C2 plus C3. Continuing on, we would have 8 equals 2C1 plus 2C3. And lastly, -1 equals C1 plus 2C2. This puts us into an augmented matrix. So for our columns C1, C2, C3, and then we have our constants, -1, 7, 8, and -1. our first column for C1s would be 1, 0, 2, 1. Next, for column C2, we'll have a 2, negative 3, 0, 2. And for the C3 column, we'll have a 0, 1, 2, 0. I won't go through the RREF at this point, but that's the setup of how you would approach that sort of problem, and you could certainly throw that into MATLAB or other computational software to determine if the C1, C2, C3 exist or do not exist. Lastly, let's take a look at an example related to functions, and recall these are these are vectors in the space of real-valued functions. So this question is saying, can we write f of x as some linear combination, we'll call it alpha times g of x, plus beta times h of x? And you could use any scalars you want. So the question is, can we write 2x squared plus a 6x plus 7 as some scalar multiple, alpha times g, plus some scalar times h? And if we work this through, we get a 2x squared plus 6x plus 7. We get alpha x squared minus alpha, and distributing the beta, we get 2 beta x plus 3 beta. Now, let's equate any coefficients that live on the x squared term. So by equating our x squared terms, this tells us on the left-hand side, 2 must equal alpha on the right-hand side. And automatically we have alpha, so that was really nice. Let's look at our linear terms. So let's look at all of our linear terms. So looking at our linear terms, on the left-hand side we have to have 6, and on the right-hand side that must equal 2 beta, and that implies that beta should equal 3. And now let's look at our constants. Equating constants, on the left-hand side we have 7, and on the right-hand side we have a negative alpha plus 3 beta. And let's check that these choices of alpha and beta work here. So is it true that 7 equals negative 2 plus 3 times 3? Now working that out, that works. So there is an alpha and a beta. There are alpha and beta that work. And so our conclusion here is that f of x, or f, can be written as a linear combination of g of x and h of x. So we could say that f lies in the span of g and h.